My name is Pablo D Esquinazi, and I will shortly explain you the main result of the studies included in the manuscript. In the last 40 years, there were several reports of not always well-reproducible results suggesting the existence of superconductivity above room temperature in graphite. Reproducible results were obtained in highly oriented pyrolytic graphite samples, indicating the existence of granular superconductivity, in some cases at temperature above 100 Kelvin. Nevertheless, till now there was no report on the existence of a critical temperature. This is the main aim of the studies we have done. Let us start with the resistance versus temperature of a bulk natural graphite sample from Brazil. Here we see the typical metallic-like resistance of graphite. We note that this metallic response is not intrinsic of ideal graphite, but it is due to the internal interfaces most of the bulk graphite samples have. For magnetic field applied normal to the graphene planes and interfaces, we see the typical giant metal-insulated transition, which in this crystal is especially large. We are interested in the region above 300 Kelvin. Measuring not in sweeping mode, but waiting at each point 5 to 10 minutes for equilibrium, we identify a clear transition in the resistance, here shown normalized by its values at 380 Kelvin. Applied field of the order of 0.5 Tesla do not shift clearly the transition to low temperature. Note that at higher fields, the large magnetoresistance at these temperatures makes the identification of the transition more and more difficult. If we subtract a linear temperature background, we get a zero field the following curve. The transition in the resistance is accompanied by the start of a hysteresis in the magnetization, as can be seen in this figure. That the transition is very probably related to the onset of granular superconductivity, we mean Josephson-coupled superconducting grains, is suggested by the change in resistance with field. We see a relatively large and positive change in the resistance at low fields and temperatures below the transition temperature. Note the clear irreversible behavior. Important is to note that this behavior can be only observed if we cool the sample at zero field from a temperature at or higher than the transition temperature. The behavior observed in the resistance at field of a few Ørsted and its remnants are typical for Josephson-coupled superconducting grains. Here we show how the remnants increases the higher the maximum field applied. This remnants does not decrease if we change the field direction. Furthermore, we found clear evidence from X-ray diffraction for the existence of broad regions with rhombohedral stacking order inside all the samples that show the superconducting-like behavior. For example, in this spectrum taken from a highly pure graphite powder. The red labels correspond to the rhombohedral stacking order. We see that most of the main peaks coincide with the common and main stacking order of the hexagonal Bernal phase. The Bragg peaks that do not coincide have an amplitude 1000 times or even smaller than the main Bragg peak. This could be one reason why this rhombohedral phase was not really taken into account in most of the transport literature of graphite. The pictures taken with a scanning transmission electron microscope reveal the minor rhombohedral phase appears to be well ordered and embedded in a matrix of Bernal stacking order, with well-defined interfaces. Here another figure of a different part of the same natural graphite sample. The interfaces between rhombohedral and Bernal may be of importance for triggering superconductivity in graphite at very high temperature, as this theoretical result of the superconducting order parameter as a function of the position in a three-layer system with a rhombohedral phase in the middle suggests. The large enhancement of the order parameter at the interfaces is mainly due to the existence of a flat band at the rhombohedral surface. Here are the main conclusions. Thank you very much for your attention.